Hello friends, I am Dr. Sudhan Sharma from School of Computer Information Science in Indira Gandhi National Open University. And in our last sessions, we had already covered about sequences and series. In those sessions, we had discussed about arithmetic progression, geometric progression, and we have also learned about harmonic progression. Also, we understood about how to find the sum of n natural numbers, square of n natural numbers, and cube of n natural numbers. Now, we are going to a next session of block 2, and this is unit 2 of block 2 of BCS 012, which is related to complex numbers. This is an introductory session wherein we are going to understand what complex numbers are, and after understanding the complex numbers, we will in the subsequent session we are going to discuss about how to represent them in a diagrammatic manner, what is the graphical representation of the complex number. So, let us begin with the objectives of the today's session are to understand the complex number and to perform the algebra of the complex numbers. Thereafter, in this session, we are supposed to learn how to determine conjugate and modulus of the complex number. Now, so far as formal definition of complex number is concerned, a complex number is any number that can be put into the form a plus bi, where a and b are the real numbers and I is the square root of -1, that it represents the complex number, and a plus bi represents the standard form of the complex number. The number a is the real part and the number b is the imaginary part, and usually we denote it by the alphabet z. That means generally we say z is equal to a plus bi, and the real part of the z, that is a, is expressed by r e z. You can say that just this REZ represents the real part of the imaginary number z, and IMZ represents the imaginary part of the complex number z. So, as to have a better understanding, say we are having an equation x square equal to 4. Now, we are supposed to find the solution of this equation. Then the solution of this equation will be x will be equal to plus minus square root of 4. That means we will be having plus minus 2 as a solution. But what if the equation is x square is equal to -1? Then we are going to imply that the solution will be is equal to x is equal to square root of -1 and minus of square root of -1. Now, square root of -1 is a complex entity, and that is why it is represented by a new number named iota and represented by I. And that is why, because this entity square root of -1 very frequently occurs in mathematics, that is why formal name is given to it iota, and it is square root of -1. And iota square, the normal algebraic rules are applicable onto this I, that is square root of -1, that is I square is equal to -1, and you will find that I square is equal to -1, therefore I cube is equal to minus of iota. Since I is equal to square root of -1, I square turns out to be -1 and I cube turns out to be I square into I, that is I square is minus I. So, I cube is minus of iota. On the same lines, you will find that on the even values, say I4 is equal to 1, I to the power 5 is equal to I, and you can find n number of values over here. Again, I to the power -1, that is I to the power -1 is 1 by iota, and that turns out to be minus iota, and iota to the power -2 turns out to be -1. So, iota square 1 iota to the power -2 is -1. So, we will solve these values, and we will learn more about complex numbers in the subsequent slides. Now, let us continue our discussion towards the algebra of complex numbers. Now, the two complex numbers are said to be the first and the foremost important thing to understand, that when the two numbers are said to be equal. So, the equality of two complex numbers is related to the when their real part and their imaginary part are equal. That means if Z1 is equal to A plus Bi, and Z2 is equal to C plus Di, be two complex number, then Z1 is equal to Z2 implies A is equal to C and B is equal to D. We can apply this understanding to solve some of the numericals. For the better understanding, the example is given over here. First example is find x and y if 3x plus 4 is equal to 12 minus 8y. Now, comparing the values, you can say that uh, 3x is equal to 12 and 4 is equal to 8y. Now, that means by solving you can get x is equal to 4 and y is equal to 1 by 2. So, you for better understanding, say I write 3x plus 4i and 12 minus 4yi. So, that means now it is a complex number. So, comparing the real part, that means 3x is equal to 12. Comparing the imaginary part, that is 4 is equal to 8y minus 8y. Then you can say that the real part of solving, we get x is equal to 4 and we get y is equal to minus of 1 by 2. On the same lines, if we are given say 4a minus 3 plus 7i and 5 plus 2b minus 1i be two complex number and they are equal, then comparing the real and imaginary part, we will get 4a minus 3 equal to 5. So, on the same lines, comparing the imaginary part, 7 will be equated to 2b minus 1. 7 is equal to 2b minus 1. So, that means a is 2, solving 4a minus 3 equal to 5, that this implies 4a is equal to 5 plus 3 equal to 8. That is a is equal to 8 by 4, that is equal to 2. And the same line, 7 is equal to 2b minus 1, that means 2b is equal to 7 plus 1, that is equal to 8. This implies b is equal to 8 by 2, that is equal to 4. So, a is equal to 2 and b is equal to 4. By applying the understanding of the equality of the complex number, we can easily solve the problems. Now, next important concept is about the addition of complex numbers. So, we can perform the addition operation on the two complex numbers, say Z1 is equal to A plus Bi and Z2 is equal to C plus Di. Then Z1 plus Z2 can be obtained by adding the real terms and the imaginary terms altogether. Likewise, over here A and C are the real terms of Z1 and Z2. So, they are added all together to form the real term for the sum Z1 plus Z2. B and D are the imaginary terms. So, B and D are added all together to form the imaginary term of the complex number Z1 plus Z2. Now, let us solve some of the illustrations are given over here, that 3 plus 4i plus 7 minus 6i. So, real terms 3 and 7 are to be added, 3 and 7 are to be added, and the complex term, that is 4 and minus 6 are to be added, that is plus 4 and minus 6. That means minus 2, 4 minus 6 is minus 2 and 7 plus 3 is 10. So, the new complex number is 10 minus 2i. I hope you understand what is about the addition of the complex number. On the same lines, you can perform the subtraction of the complex number, wherein say Z1 and Z2 are the two complex numbers, that is A plus Bi and C plus Di. Then the difference of two complex numbers, that is Z1 minus Z2, is actually equivalent to summing of the Z1 plus minus of Z2. So, you can explicitly write the expression Z1 minus Z2 as A plus Bi plus minus of Z2, wherein the polarity of the sign will be changed, minus C minus Di, and performing the addition operation again, you will find A minus C plus B minus D. On the other way, you can say that you are supposed to subtract the real components and the imaginary components separately, as we did in the case of addition, wherein Z1 plus Z2 turns out to be A plus C plus B plus D I. So, Z1 minus Z2, Z1 minus Z2 is nothing but performing subtraction operation for real part and the imaginary part separately, you will get this. So, Z1 plus Z2 and Z1 minus Z2, and you can again perform the illustrations are self-explanatory, wherein you are subtracting the real component and the imaginary component separately. So, 3 minus 7 and 4 minus or minus 6, so it will turn out to be plus. So, that is why it is minus 4 plus 10I. So, I hope you understood what do we mean by the subtraction of two complex numbers. Now, the multiplication of the complex number. Now, in this case, you are supposed to understand a bit, because uh, over here I square is equal to minus 1 is an important identity which we are going to explore. We learned that I is equal to square root of minus 1, and I square will be square root of minus 1 into square root of minus 1, that is equal to minus 1 only. So, how we are going to use this entity? Let us understand. Say Z1 is a complex number A plus Bi, and Z2 is a next complex number C plus Di. Now, Z1 into Z2. Now, how you are going to get Z1 to Z2? Just by simple multiplication. Z1 is A plus Bi and Z2 is C plus Di. So, opening the braces, it will be AC, this into this, plus this into this, plus A into Di. Now, this into this, plus B into Ci, plus this into this, that is B into Di square. So, what it turns out to be, that is AC plus ADI plus BCI. Now, I square is minus 1. So, this will turn to B minus of BD. Solving, you will get, separating the real and imaginary part, you will get AC minus BD plus iota of AD plus BC, and which is this expression. So, that means this is how you are supposed to perform the multiplication of the two complex number and get the expression Z1 into Z2. Now, let us understand this by performing in calculation. Here 3 plus 4I and 7 minus 6I are the two complex numbers which are given over here. So, AC, this into this, BD, now minus of BD, so this into this. So, you will get, by performing the same way, performing the calculation in this manner, you will get, first term is 7 into 3, that is 21. Just wait. So, 7 into 3 is 21. Again, 3 into 6 is 18. So, 18I. 4 into 7 is 28. So, 28I. 4 into 6 is 24I square. So, which is minus 6. So, minus 24 and I square is minus 1. So, minus into minus is plus. So, that is why it turns out to be plus 24. So, 21 plus 24, 21 plus 24 is 45, and 28 minus 18 is 10. So, 10I. So, the entire answer turns out to be 45 plus 10I. I hope you understand how the multiplication of the complex numbers is to be done. Now, there is an important concept which is known as multiplicative inverse of a non-zero complex number. That means a complex number, as we found the inverse of a when we were solving the system of linear equation Ax is equal to b, we learned x is equal to A inverse b. That means, and we also solved A inverse of A is equal to identity matrix. That means it will give you the answer 1. On the same lines, which complex number should be multiplied so that we get the answer 1? That is 1 plus 0 I. That means whose imaginary part is 0. Only 1 is the value. So that z value is nothing but the multiplicative inverse. Multiplicative inverse. So say a plus ib is a complex number, and there exists a complex number x plus iy such that a plus ib into x plus iy is equal to 1 plus 0 I. Then x plus iy is nothing but the multiplicative inverse of a plus ib. I hope you understand that there are two complex numbers such that the product of the two is only a real number whose value is only 1. So that means the other number x plus iy is cancelling. Actually, this is, say, you can say that a upon a is equal to 1. This cancels out. So that means a inverse into a is equal to 1. So that's why this is inverse. This is multiplicative inverse of a. So on the same lines of action, we are going to have the multiplicative inverse of the complex number a plus ib. So let's apply the understanding of multiplicative inverse to solve numerical, that how the multiplicative inverse are determined. Say a plus ib and x plus iy are two complex number and their product is 1 plus 0 I. So on the basis of multiplication, when we are opening the braces, as we learned how to multiply the two complex number, after multiplying these two complex number, we will be getting the answer ax minus by plus iota of ay plus bx, and this answer is equivalent to 1 plus 0 I. So comparing the real values, we will get ax minus by equal to 1 and ay plus bx is equal to 0. Now rearranging the expressions, we will get ax minus by minus 1 is equal to 0, and over here we will get ay plus bx is equal to 0. Solving these equations, you will get the answer x is equal to a upon a square plus b square and y is equal to minus b upon a square plus b square. That means the multiplicative inverse x plus iy is the multiplicative inverse and its value is a upon a square plus b square minus iota of b upon a square plus b square, where a and b are the real and the imaginary part of the number a plus iota b. So this is how we calculate the multiplicative inverse, but just to understand how this solution is achieved, how we got this solution by solving this equation, let's understand in a better way. So in order to solve, because multiplicative inverse is a plus ib, when multiplied by a plus ib, then it will be equal to 1 plus 0 I. So that means multiplicative inverse, this is nothing but x plus iy, because this is the inverse of a plus ib. So we are supposed to find this is equal to, in fact, x plus iy. So we are supposed to find this value. So multiplying 1 over a plus ib with a minus ib, which is the conjugate of a plus ib. Conjugate is, say we are having a complex number z is equal to a plus ib, then its conjugate z bar will be equal to a minus of ib. The sign of the imaginary part is reversed, is changed. So this is, by multiplying it with its conjugate, we will get the value this. Now, on the same lines, when you are going to multiply a plus ib with a minus ib, it turns out to be a square plus b square. How? This will a plus ib a square into minus of ib plus of ib and minus of I square b square, minus of I square b square. So, I square is minus 1. So, that is why this will cancel with this. So, this will be a square plus b square. So, a square plus b square. So, that means this expression is nothing but equal to a square plus b square. So, that is how our this x plus iy, which is equal to 1 over a plus ib, multiplying and dividing it with its conjugate and solving, you are getting the expression x plus iy is equal to a minus ib upon a square plus b square. Separating the real and imaginary part, you will find that x is equal to a upon a square plus b square and y is equal to minus of b upon a square plus b square. And that means x plus iy is our multiplicative inverse. And this is what the solution was. X was a upon a square plus b square and y was minus b upon a square plus b square. Same solution we achieved over here. I hope you learned how to solve the equations to get the multiplicative inverse. Now, let us learn about the division of complex numbers. Say Z1 is x plus iy and Z2 is a plus ib, then Z1 by Z2 will be given by x plus iy by a plus ib. Now, again on the same lines, because we are having one complex number in the denominator. So, in order to solve this, we are supposed to multiply this with the conjugate of a plus ib, that is a minus ib and a minus ib. Multiply and divide by a minus ib, that is the conjugate of a plus ib, and solving the denominator, you will get it equal to a square plus b square. So, that means the overall expression turns out to be x plus iy into a minus b, which is this expression, upon a square plus b square, which is obtained after the solution after solving a plus ib into a minus ib. And thereafter, just by multiplying and separating the real and imaginary part, you will get this expression. So, this is obtained after performing the division operation on the two complex number. So, let us solve some numericals and for better understanding. Say over here, if we are given 1 minus I upon 1 plus I whole to the power 100 is equal to a plus ib, then show that a is equal to 1 and b is equal to 0. Now, it is very simple. What you are supposed to do? In denominator, we are having 1 plus I. So, we are supposed to multiply with the conjugate of 1 plus I, that is multiply and divide by the conjugate of 1 plus I, that is 1 minus I. So, we multiplied and divide with the conjugate of 1 plus I, that is 1 minus I and 1 minus I. Performing the multiplication and division and thereafter performing the multiplication at the numerator and denominator, you will get 1 square minus I square in the denominator, and it is the square of 1 minus I whole square. Solving a square using the identity a minus b square, that is a square plus b square minus 2ab, you will get the expression 1 minus 2i plus I square, and I square itself is minus 1. So, I square is minus 1. So, that is why this one and this one will cancel out, and what you will get is minus 2i upon 2, and 2 and 2 again cancels, and what you will get is minus of I. So that means I to the power minus 1 upon 1 plus I is finally solved to the value minus I, is finally solved to the value minus I. That means to the power 100 is minus I to the power 100, and minus I to the power 100 turns out to be 1. How it turns out to be 1? Because minus I, in the beginning we had discussed about I square is minus 1 and so and so. So over here we are just briefing out that how the powers of iota are varying. Minus I to the power 1 is in fact minus I. Minus I square is minus I into minus I, that is I square, and that is minus 1 only. Minus I cube is minus I, that is I square, minus I into I square, which is this value. So this is minus 1 value. So what you will get is minus I into minus 1 is nothing but I. And I to the minus I to the power 4 on the same lines turns out to be 1. So it is observed that the power repeats every 4 times, and when we divide 100 by 4, we got the remainder which is 25. We got the value quotient 25 and the remainder is 0. That means minus I to the power 100 corresponds to minus I to the power 4. That's why minus I to the power 100 turns out to be 1 only, because minus I to the power 4 turns out to be 1 only. So we had discussed also about the conjugate part of the complex number. We learned that if z is equal to a plus ib, then the conjugate z bar is equal to a minus ib, and this is represented by z bar, which is mentioned over here. 2 plus 3i, the conjugate of this will be expressed by 2 plus 3i bar, and wherein the final solution is that the complex entity, the sign of the complex part is changed. So 2 plus 3i, the conjugate of this is 2 minus 3i. 3 minus 4i conjugate is 3 plus 4i. I hope you learned about what is conjugate of a complex number, and till the moment you are able to understand how to perform addition, subtraction, multiplication, division of the complex number. Now there are some properties about the conjugate of the complex numbers, wherein the conjugate of a conjugate is nothing but the complex number itself, and you are having, say, uh, conjugate of the product of two complex numbers is the product of the conjugate of two complex numbers, and conjugate of the division of two complex number is the division of the conjugate of two complex numbers. Similarly, z1 plus z2 bar is less than or equal to this z1 bar plus z2 bar, and these are the properties which are listed into your self learning material also. You can refer to these properties. And now the next important concept about the modulus of complex numbers is how to find the modulus of a complex number. The modulus of complex number is actually the square root of the square of the real and the imaginary component of a complex number. Say z is equal to x plus iy, then the modulus will be equal to of this complex number will be equal to x square plus y square. So if z is equal to 2 plus 3i, then modulus of z is equal to square root of 2 square plus 3 square, because real component and imaginary component are 2 and 3. So that turns out to be 4 plus 9, because 2 square is 4 and 3 square is 9, that is square root of 13. 9 plus 4 is 13. So this is about the modulus of the complex numbers, and there are some properties about the modulus of the complex numbers. Likewise, the z1 and z2, as we were having the properties about the conjugate of the complex number, The square of the modulus is product of complex number and its conjugate, and the modulus of the conjugate of a complex number is equal to the modulus of the complex number itself. And this is a triangular inequality wherein modulus of z1 plus z2 is less than equal to modulus of z1 plus modulus of z2. You can refer to these properties. These properties are very much mentioned into your self-learning material. I advise you to go through your self-learning material in parallel with these videos for better understanding. Then only you will be able to understand that how the things which are delivered in these sessions are in resonance with the self-learning material. So, I advise you to go through self-learning material also. These are the properties, and we are now going to apply these properties to solve some of the numericals. Likewise, a question is given over here is that say a plus ib is not equal to 0, show that a minus ib upon a plus ib is equal to 1. Now, say complex number z is equal to a plus ib, then its conjugate will be z bar is equal to a minus ib. And we learned that the modulus of the complex number is equal to modulus of its conjugate. So, and we also learned that the modulus of the division of two complex numbers is equal to the division of the modulus of two complex number, and that will turn out because z is equal to z bar modulus of z is equal to modulus z bar. So, these two will cancel, as a result of which the answer will be equal to 1. So, uh, we can say that 1 is equal to complement of conjugate of z divided by modulus of z, modulus of conjugate of z divided by modulus of z, which is equivalent to z bar upon z. And because z is equal to a plus ib, so conjugate of z will be equal to a minus ib, and overall conjugate and overall modulus will be equal to modulus of a minus ib upon a plus ib. So, this proves this identity. This is shown over here that a minus ib upon a plus ib is equal to 1. Or you can simply say that conjugate of z divided by z, the overall modulus turns out to be 1. So, let us understand through one more example. In this example, x plus iy is equal to square root of a plus ib upon c plus id, and we are supposed to verify that x square plus y square is equal to square root of a plus b square upon c plus d square. Now, given x plus iy is equal to square root of a plus ib upon c plus id, by squaring both sides of this expression, you will get x plus iy square is equal to a plus ib upon c plus id. Now, taking the modulus, x plus iy whole square's modulus will be equivalent to the modulus of this expression, which is written over here. And we in the last numerical we saw that modulus of z1 upon modulus z2 is equivalent to modulus of z1 upon z2. Applying this concept, modulus of z1 will turn out to be, because z1 is equal to a plus ib, so modulus of z1 will turn out to be square root of a square plus b square. So, and similarly z2 is equal to c plus id. So, therefore, modulus of z2 will turn out to be square root of c square plus d square. So, substituting the values over here, you will get square root of a square plus b square upon c square plus d square. And again, solving this square part, the square and the square root will cancel, and you will find that x square plus y square turns out to be square root of a square plus b square upon c square plus d square. So, I hope you learned about the conjugate of complex number, modulus of the complex number. We had also learned about the algebra of the complex numbers in this session, wherein we learned about what do we mean by the equality of the complex numbers, how to perform the addition and subtraction operations in the complex number, how to perform multiplication and division of the complex number. And finally, we also learned about how to find the multiplicative inverse of the complex numbers. In the subsequent session, we are supposed to learn about the Argand diagrams, wherein we are supposed to learn how to express the complex number in a graphical manner. And apart from this, we are also going to learn about the polar representation of the complex numbers. This session is up to this much only. Thank you very much.